Okay, let's take a look at number 10 in section 4.5. Carbon-14 occurs in living organisms with a fixed ratio to non-radioactive carbon-12. After a plant or animal dies, the carbon-14 decays into stable carbon with a half-life of 5,730 years. When samples from the Shroud of Turin were analyzed in 1988, they were found to have 89.7% of their original carbon-14. How old were those samples in 1988? And we're going to round to the nearest year. Okay, to write our formula, this is going to be an exponential decay function. It's going to be of the form Q of t is equal to Q naught times 1/2 or 0.5 to the t over h. Okay, and this is if you know the half-life of a particular substance, you can substitute it for h. Okay, so in this case it's Q of t is equal to Q naught times 0.5 to the t over 5730. Okay, well the goal is to find out how long it took for the amount of carbon-14 to decay to 89.7% of the original amount. Even if we don't know how much the original quantity was, but there's this relationship between the initial quantity, Q naught, and the later amount, whatever that Q of t value is. Okay, so in that relationship is this factor of 0.897, okay, 89.7%. So write it as a decimal, and we're going to multiply Q naught by that. Okay, and now we see that the Q naughts cancel out, and so it doesn't matter how much carbon-14 there was initially, that this relationship is still the same between the initial and the later amounts, that factor of 0.897 holds. Okay, for instance, if you want to use an initial quantity of 1,000, you could then say that Q is 897. And either way, when you divide them, divide 897 by 1,000, you get this 0.897. And so here's just kind of the faster approach, is to use this ratio, which happens to be the decimal version of this percentage. Okay, so now our goal is to solve this equation. Okay, and we can do this one of two ways. We can solve it by rewriting this equation, converting it to a logarithm. And the other option is to use a graph and find the intersection of two functions. Okay, so using a logarithm, okay, we have log. Whatever the base of the power is going to be the base of the logarithm. So log base 0.5 of whatever kind of the answer to the power, 0.897, is equal to whatever the exponent is. And that's this ratio t over 5730. Okay, we still want to isolate t, and so t is going to multiply both sides of this equation by 5730. And we get t is equal to 5,730 times log base 0.5 of 0.897. Okay, and lastly, we just need to get a decimal approximation. And so we're going to go to the calculator. I'm going to type 5730. Okay, but then we can use the change of base formula to enter this logarithmic expression. So we can just type log of 0.897, and this log key on the calculator has a base of 10. So log of 0.897 divided by log of 0.5. And it says round to the nearest year, so about 899. Okay, so it will take about 899 years for this amount of the carbon 14 to have decayed, just a little bit over 10%, to have decreased, and 89.7% of it to remain.